Yeah, I don't know what to do.
I think it's just the permissions. Probably you have to go to settings and allow
Okay.
privacy and whatever it is. What is it? Privacy and security. Yeah, privacy and security on the left hand side.
On the left.
Down,
Ah, yeah. Okay.
and you allow.
So it's through Chrome, I guess. So.
Still Chrome. Okay. Yeah.
But I don't see.
Yeah. Go back to Jitsi.
To where, sorry?
To the browser. Go back to go to the ellipsis.
The where, sorry? Down.
Right, so just say the red box.
Yeah, here you go.
Yeah. Second.
Ah, yeah. Okay. Enable video. Nice. Yeah.
Cancel. I don't think this is okay. Try again. Permissions. Please remove the trade.
Can you share it to share it to Leo and the user and the computer.
It's going to be tricky because it's like an Apple thing, so my equations won't come through. I don't think. I could maybe I could send it to someone with an Apple computer. I think my equations will get messed up if I send it.
Okay. Can I share the screen? Let me check.
Yeah.
Maybe you said no when you asked me to share screen. Yeah. So
Okay. Well.
This video. I can share. It seems I can share.
Okay, I'll put it in the.
It's a good suggestion. Do you have a browser?
I don't know. Safari or maybe.
It's a good point. So,
Okay.
Just copy the link from.
Okay, good idea. Oh, wrong name. Doesn't matter. Yeah.
Allow to share screen? Yeah.
Okay, it looks like it might work.
I think you probably said no when you were prompted to do it on whatever it was.
Yeah.
Okay, great.
Okay, so is it showing?
Yep.
All right. Okay. Well, hey guys, thanks for having us in Palermo. Beautiful city, by the way. We've been to the beach. I've had brioche gelato, and I never want to go home now. But a little bit about our home. So this is our quantum information group here in Nottingham on the left, run by Gerardo Desso there on the right next to Federico. This is our campus here in the top right. We have a nice lake. And so a few things about Nottingham. We have the oldest pub in the UK and also the National Ice Centre. So if you like ice skating, old pubs and quantum information, please come visit us. Okay, so I'll tell you a little bit about my work in super resolution of surface roughness estimation. So a little overview for this talk. So first I'll give you some motivation for the project. I'll tell you a little bit about quantum parameter estimation. I'm going to tell you a little bit about how we model a rough surface. Then I'm going to tell you about the ultimate limits we found on the information you can get about a rough surface. And I'll tell you a little bit about some measurement schemes you could use to image the rough surface. So these are classical imaging and mode sorting, or spatial mode demultiplexing. And then I'll tell you a little bit about the future outlook of the work. So, who cares about surface roughness? So, I mean, I haven't really done any market research, but off the top of my head, engineers involved in precision manufacturing, for example, space shuttle designers, right? If you were going to design a space shuttle, you might want to know exactly how rough your surface is, such that you could calculate your coefficients of friction and maybe not burn up upon re-entry into the atmosphere. Another thing that, maybe for Formula One, right, the tyre manufacturers might want to know exactly how rough their tyres are, such that they don't slip and slide all over the track. And then even in microelectronic circuit design, right? Because if you're putting these really small, these really fine silicon wafers, you might want to know exactly the defects in the wafers, such as to not incur issues in your circuitry. So now a little historical overview. So consider an imaging system, right? So this is basically an object that emits light, like a point source, and a lens that focuses this light onto an imaging plane, and then someone that is going to view the light, so like the eye on the right there. In 1879, Lord Rayleigh heuristically established a limit on the resolving power of an imaging system. He said, given two point sources of light separated by a distance theta, the smallest separation at which you can still resolve the two, i.e. separate them, is approximately 1.22 times the wavelength of the light divided by the diameter of the lens, or the circular aperture that focuses the light. And you can see the manifestation of that when we look at the intensity profiles of two light sources. We can see that as we bring them closer together, they kind of start to merge into one. And at a certain point, namely 1.22 lambda over d, you can no longer distinguish the two, okay? The issue with this is it's not very rigorous. It doesn't really tell us very much about what resolution actually is. So thankfully, in 2016, Mankade Sang used quantum metrology to formally benchmark resolving power. And here, he described resolving power in terms of the error that you would incur in estimating separations between two light sources. And he showed that the error is inversely proportional to the amount of information that can be inferred about parameter theta, about the separation. And what he found is that this error, and the main result is that the error is bounded below by, bounded below in this thing called the Kramer-Rao bound, which gives you your minimum error when estimating the parameter theta. It says that it's inversely proportional. Yes, it's equal to the inverse of this quantum Fisher information that he found to be 1 over 4 times the variance of some generator squared, generator involving all the kind of physics about the imaging system. He also found a measurement scheme that could reach this limit, but I'll talk about that later. Okay, so how about a little background about quantum statistical inference. So let's consider the space of density operators parameterized by a vector theta. This space is going to represent our physical system, which depends on the parameter. Okay, so for example, this will be, in the previous example I gave of the two sources, this will represent the light coming from the two sources, and that is encoded in which the parameter theta, the separation, is encoded into it. Now we consider a POVM, xi, as a set of measurement schemes. So this set, represents our measurement scheme, whatever that may be. And what we find is that a measurement in this xi basis yields a probability distribution P of x, the results of the random variable, given some parameter theta. So now arise two key questions in metrology. Question 1, given a measurement scheme xi, which yielded the distribution P, how well can one distinguish between two neighboring points? Alternatively, one can rephrase this as what is the error that I would get when I estimate the parameter theta using this measurement scheme xi? And the second question, out of all measurement schemes xi, what is the most sensitive measure of distinguishability between neighboring points? This can be rephrased as what is the absolute lowest error I can ever hope to achieve when estimating the parameter theta? So let's try and answer these questions. The answer to the first question is the classical Fisher information. Right? And so if we consider a probability space with parameterized curves P and a tangent space spanned by these score functions, which are derivatives of the natural logarithm of P, and basically give you an idea of the landscape of this distribution space, and kind of tell you the sensitivity of P to, I'll tell you, if you go up a hill, it tells you, if you change theta, do you go up the hill of probabilities or do you go down the hill of probabilities, etc. And what you can, the quantum Fisher information is defined as the expectation of the square of these score functions. And in turn, this finds itself in the Kramer-Rao bound, which basically bounds the error in estimating theta by below. So it says that, we have a lowest error in estimating theta, and the Fisher information is either always equal to it or above it, but the inverse of the Fisher information. So basically, the Fisher information what it tells you is a measure of sensitivity of your measurement scheme to the parameter. And you want your measurement scheme to be as sensitive as possible to the parameter. You change your parameter a tiny bit, and your measurement scheme gives you wildly different results. So the answer to the second question is the quantum Fisher information. And so here, if we consider the state space with the parameterized curves rho of theta, and we define a symmetric logarithmic derivative, which is essentially like a non-commutative version of this score function, and it's defined here implicitly in this Lyapunov equation. Then we can define the quantum Fisher information as kind of similar to essentially the same as the classical Fisher information, which is the trace of the square of this symmetric logarithmic derivative. Or perhaps what's a more telling definition of it is that the quantum Fisher information is the maximization of the classical Fisher information over all possible measurement schemes. So, you imagine all possible measurement schemes. We want the classical Fisher information that is associated to the measurement scheme that maximizes that classical Fisher information. And again, so this quantum Fisher information is the information that saturates this Kramer-Rao bound. Okay, so it is the inverse of it is equal to the error in estimating the parameter theta, and all classical Fisher informations are inverses of the classical Fisher informations are greater than or equal to it. All right. So let me tell you a little bit about how we might model a rough surface. So here's a rough surface on the right here, kind of a crazy one. In principle, what we would like to do is to consider a continuous 2D profile of single photon emitters. So if you imagine like a mountain range, like here on the right, and imagine a little circular area, and we could move it around, and so we would have a radial area, and also axially away and towards us. And we would describe the state of the optical system as a statistical mixture of little photon emitters on the surface. All right. Where each photon emitter, the state of the light of each photon emitter is essentially a pure state displaced, where the pure state is the state of the light at the focus of the imaging system, of the lens. Okay, so we have a lens, and the lens is a focus. Put the focus on the surface, and then the state of light emitted from this focus is pure. And if you move the state slightly, of the source slightly, the state changes based upon these generators Gx, Gy, and Gz. Okay. So that's a very near future goal. All right. The reason why this talk was titled had this looking down the rabbit hole thing. It's not because I'm going to talk about any crazy conspiracies or anything like that. It's because we are just at the moment considering sources along the optical axis. So, in a line, kind of down a rabbit hole, if that makes sense. Along the z-axis, basically, right? Just like that. Yeah, okay, I'll show you that. And here we can describe the state, similar to before, we describe the state of light as a statistical mixture of these states displaced from focus in Z, where the displacement of the state is generated by this G, and the G we assume satisfies this paraxial propagation. Okay, so basically what this means is we're going to consider the light to be Gaussian, the beam to be Gaussian. And we define surface roughness as the standard deviation along Z. So the square root of the second moment minus the square of the first moment, where the moments are given by these in this integral. So let's place a limit on how well we can estimate surface roughness. So thankfully, it's very nice, but our system is readily in the Krauss representation. So we can use this nice trick and basically relate the quantum Fisher information to the fidelity via the Buell's distance. It's really cool, actually. The fidelity here is given by the trace norm of this thing called the metrology matrix. And the metrology matrix elements are, just the trace of these Krauss operators, one of them displaced slightly in the parameter. And what we find is that the quantum Fisher information for the mean and the standard deviation of sources along Z is constant and equal to 4 times the variance of the generator G. So that was nice. So now that we have our upper bound for delta G squared, let's see if we can reach it. So let's talk about some measurement schemes. So the first measurement scheme I'm going to talk about is called direct imaging. And this is really just measuring the intensity of the received field, or measuring the state of light on a position basis. And we will assume a Gaussian beam for all our light. So, quick interlude. This becomes very difficult because actually, if you imagine you have all these sources with little distances, you have lots of parameters to estimate, and then you want to convert all these distances into moments, first, second, third, etc. But really, you only care about the second. Right? So it would be great if we had a way to do this estimation theory with potentially infinite parameters, but only worry about a finite subset of them. So well, if we have infinite parameters, but we only care about one, so we can partition our parameter into this vector of a single parameter, and the rest we call them nuisance parameters. So thankfully, again, Mankei Tang came up with this great formalism. And the trick here is to treat random variables and their functions as elements in a Hilbert space, in which we define the inner product as this expectation with respect to the intensity of the light in a given basis x. And then we treat our parameter of interest as a functional of this intensity in the x basis. And then we search for something called an influence function, which is defined implicitly in this functional gradient. In doing so, we can define the Kramer-Rao bound as the norm of the projection of this influence function onto a tangent space spanned by score vectors. Okay? And this gives us yes.
So you're saying you don't care about this.
Yeah, we don't care about the etas, we just want one single beta.
So what are these equations? H1 and H2 relation?
H1 and H2 in relation to eta. I mean, they're quite general, but they can, the case it's useful, they will be maybe score functions. Score vectors, score functions. Yeah. Score functions relating to the parameter beta.
Okay. So then what do you do?
What do you want to do with them? Well, the point is you derive this Kramer-Rao bound, which is the norm of these, essentially the norm of these of this influence function that is related to the parameter of interest. And then you can calculate general formulae for the Kramer-Rao bound, just for one single parameter that's of interest. Yeah.
Sorry, I didn't quite get, so you're saying the beta is just again, right? What do you mean by that here?
So I don't think it's quite an estimator, it's called an influence function. It tells you how much your measured data influences your error, how much it contributes to your error, essentially.
How do you compute it?
How do you compute it? You compute it. So it appears if you can basically get this some functional gradient of the parameter of interest in this form of the integral, then you have it.
So you have to solve that.
Yeah, you kind of have to get that equation when you have it. Yeah.
Where H here is what is
H. So H. Yeah, H I think can almost be anything. Like in some cases it can be the score function, and this gives you a result. Otherwise, H can just be 1, actually, like just like an identity map. It doesn't. Yeah.
It's a weight that depends on the task. Or
Is it what? Sorry.
it's a weight parameter that depends on the task. Like depending on the task, you have.
I suppose. Yeah. It depends on the.
F is the parameter you want to estimate. Understand?
But beta is the parameter you want to estimate. Yeah, F is the weighting. Is the. So
The probability distribution.
yes, exactly. Yeah.
So you do not know eta, you don't want to know.
You don't.
At least you have some knowledge of the distribution of these values.
I don't.
Because of course you don't know eta, otherwise it would be a single part of the distribution.
Yeah,
You somehow do some averages of these and so on.
yeah. You don't know it, for sure you don't know it. Whether you have some information about its distribution or not actually sure. I don't think so. I don't think you need to. I don't think you need to have knowledge of its distribution.
Okay.
I don't think. Maybe I'm wrong though, I could be wrong. But I don't think so. I'll find out. So now let's come back to direct imaging. If we use this formalism, then we can derive this Kramer-Rao bound as this equation here, and the important thing, the interesting thing, is this C matrix that maps. So you have an object, and this object is imaged, and then you have an object distribution, and this is imaged onto an image distribution, and you have theta is the object distribution moments, and phi is the image distribution moments. C maps the object moments to the image moments. And what we find is that C is non-invertible. And the reason why is that the kernel is spanned by these odd-ordered moment basis vectors, which tells us that direct imaging is fundamentally incapable of detecting odd-ordered moments. Moreover, we find that in the limit of small z, the even moments greater than or equal to the second one are constant, and this means that the Fisher information for even ordered moments greater than or equal to 2 is constant, and this tells us that the Fisher information for the standard deviation in the limit of small z is 0, and thus direct imaging is totally incapable of estimating surface roughness for very fine surfaces. So if you look with your eyes, you won't be able to see how rough your surface is. So thankfully there exists a proposal for a measurement scheme that does saturate this the Kramer-Rao band and can image surface roughness, and it's called spatial mode demultiplexing. And what this is essentially you consider real-valued functions that have known parity and are proportional to derivatives of the point spread function, i.e. the response of your imaging system to an impulse. And if you project into this basis, you should be able to saturate the Kramer-Rao band. And the way this works is kind of like a Taylor series expansion. If you imagine, like you displace a function slightly, then the higher order derivatives are also spread out, and as such, if you were to then take the overlap of those with the displaced function, you would get non-zero results. You would get more of an overlap.
Yeah. I think how physically you can do that?
Physically?
Yeah. Kind of 2 wiki you can conduct lab and the demultiplex work.
I don't know. Sorry. Yes, you prepare the untechnical answer I know is you prepare resonant like modes in a box, and the light couples to the modes. And I don't know actually. Yeah. I'll find out. If we consider just radial displacements, so not away or towards the viewer, but just in the tangential plane, then we can just use this real-valued Gaussian function, and, well, the situation is like this. Then we know that the Hermite Gaussian basis is sensitive to displacements like this. Okay, so here's the first formula of the Hermite Gaussian basis. However, our issue is that we are not looking at radial displacements, we're looking at axial displacements, first and foremost. And so the Gaussian basis in this case is not sensitive to axial displacements at all, blind to them. And so we consider the Laguerre-Gauss basis, which is sensitive to axial displacements of sources, which emits the full Gaussian beam. So this is the situation. And these are the base of the modes, and the first four plotted there for you. And so what we find here is, again, Kramer-Rao-bound looks kind of similar to the other one. The C matrix here in this case relates the moments of the object distribution to the intensity in the basis, the basis we choose. And we find here that the C matrix is only sensitive to even ordered modes again. And so again, we find that we find that the classical Fisher information is equal to 4 times the variance of the generator squared, which turns out to be equal to the quantum Fisher information. So we find that spatial mode demultiplexing is optimal for estimating surface roughness. So that was nice. Okay, and so in summary, we find that the information one can gather about the roughness of the surface is bounded, in the sense that there will always be errors when we try to estimate it. We find that direct imaging fails to estimate the roughness of fine surfaces, and that Spade in the Laguerre-Gauss basis is optimal for estimating the roughness of fine surfaces. So in the future, so in the very near future, we want to extend this work to estimate the roughness of a small profile. So we've done the axial displacements and the Laguerre-Gaussian basis. Now we want to extend this to the full Laguerre-Gauss basis, including the angular part, so that we can look at that little circular area on the mountain range that I told you about. And so actually, it turns out that in relation to your question about how you do this physically, I don't know exactly, but it's very hard to do. And so you kind of want to be very picky and choosy about what modes you measure. You can't do them all. So we would like to design a machine learning algorithm to predict which bases and which modes are optimal given a particular imaging system and a particular surface distribution.
Does this involve only the measurement basis or also the base in which you shine light on the sample?
The measurement basis and so how are they different? What do you mean?
Are you thinking about changing the modes you shine over your sample, or only the basis in which you measure?
Oh, only the basis modes in which we measure. Yeah.
So, in a sense, this answers the second question you were saying about the contribution. You found the optimal basis.
Yeah.
In a way, it is the answer to the question of finding the optimal basis.
So we found the optimal basis given a Gaussian point spread function. So this Gaussian point spread function is to do with the imaging system. If you were to change the imaging systems, for example, I don't know, you don't assume a Gaussian lens, then the Laguerre-Gaussian basis is no longer optimal. So it would be nice to have maybe an AI tool that could tell you, given some arbitrary imaging system, some aperture, some surface distribution, what is the best basis to measure in, and then what modes are best to measure in as well.
In a sense, the problem of finding different lines,
Yeah.
It's a typical problem of quantum metrology, which is even harder than the camera itself. So it's to find what's the best probe to achieve your task.
Yeah, I'm not really sure. So I only really think about the light as kind of originating from the distribution. I don't really think about shining it on the probe. But I guess the question of the light shining on the probe and the imaging system are intimately tied together, I think. I don't know. Yeah. Anyway, thank you.
There were some questions already, so please take any more.
Probably you said, but so what kind of actual surfaces would this framework apply? to? Like, what do you have in mind, like physically speaking, to apply this kind of framework?
Oh, like in real life?
Yes. Like, you mentioned surface, you said real surface.
I mean,
Like, what kind of system even, like, what?
yeah, I mean, the example I gave was like,
System. You know, that will matter a lot as far as like actual interaction with some system.
I mean, I'm not sure I understand the question. Like, if you look at a rough surface, if you shine light on the surface, we want to estimate the roughness of that surface. Any surface, I think. More or less. So I mean,
Actual line bouncing plus.
yeah, and also like really fine surfaces below the diffraction level. Yeah.
Okay. And so another one. So all of these is in the framework of like feature like quantities. So this is like it gives you the best estimators or whatever. Like assuming you kind of already know the parameters, right? Like it's local estimation.
Yeah.
Does that make sense for this kind of task? Because like it means these bounds apply when you kind of already know what the surface looks like, right?
Yeah, I mean, we assume that like the mean is 0.
You assume that the
The
mean
mean is 0, yeah, so it's kind of centered. It's above and below. And then standard deviation is small, close to 0.
So when you talk about the roughness estimation, you're only looking at the racks.
That's always, Praxel, yeah.
So you are not so interested in other possible directions.
Oh, the radial directions. Yeah, we are actually. That's just next. Yeah. So up till now, we've just done the axial. There's been a lot of work done on radial displacements. So I think it's just a combination of. It's all about kind of combining the two. Is the difficulty.
But that would be a multi-parameter problem.
It's it's already multi-parameter, but it's no, I see what you mean. Yeah, it would be you want standard deviation in X, Y, and Z,
Right.
rather than just Z. So yeah, it would be like a semi-parametric problem, but not quite so semi-parametric.
Yeah. Full 3 parameters.
Yeah.
So, yeah. The overall model becomes
But the fact that the quantum feature information coincides with the classical one, is it a byproduct of the fact that you emit are incoherent with respect to each other? So there is no coherence between one emitter and the next in the line.
Yeah, I think so.
Yeah. So, roughly speaking, it's basically. It's a talk on roughness, so roughly speaking is probably not the right way.
Nice. I'll use that one.
It's a classical imaging problem.
Yeah.
Okay.
Yeah, maybe we look at coherent light soon one day. I don't know.
I mean, probably if you have some degree of coherence between the different emitters, maybe you will have some surprises about what would optimize the feature information.
And actually, to tie into your question as well, if you look at what they use in general to image real microscopic things, they use these kind of interference-based lasers. This was coherent light, so I think we need to go into that.
Okay, let's start with working and laser.